Well, hi guys. We're going to have a look at graphing inverse functions and relations in this session in detail. So what is an inverse function before we even start? Well, it's the result of taking a one-to-one function and swapping x for y and y for x. As you probably already know, NB, it can only be a one-to-one function which is used to create an inverse function in the first place. E.g., if you took a many-to-one function, many x to 1 y, and you swapped x and y, you will end up with what was originally a many-to-one. Now let's swap the x and y. So there's the x now, and there's the y. So you're going to end up with a one-to-many, which is not a function, that is a relation. So it has to be one-to-one, absolutely has to be one-to-one. Because the inverse is a result of directly swapping all y values, making them x and vice versa, the original and its inverse are exact mirror images of each other about the line y equals x. For example, if we took f of x equals 2x, then the inverse would be denoted as f minus 1 of x and will be f minus 1 of x equals a half x. Now there's a graph of that. You can see that we've got, what have we got here? We've got the original, f of x equals 2x. We've got the inverse, f minus 1 of x is a half x, and we've got the line y equals x about which they reflect. Okay, and we'll just, to drive the point home, we'll just show you how you do it. If you had, for f of x, if we let y equal 2x and we swapped x and y, then you solve it for y, you get half x, don't you? Yes, so f minus 1 of x would be half x. Yes? Properties of inverses. Now these are really, really important. The domain of the original function is the same as the range of the inverse because you're swapping x and y, and vice versa. The range of the original is the same as the domain of the inverse. The x and y intercepts of the original function become the y and x intercepts respectively of the inverse. Yes, because you've swapped x and y. In addition, asymptotes also reflect in the same way. They, of course, also reflect about the line y equals x. So vertical asymptotes become horizontal. Either x equals b becomes y equals b, and vice versa. Another one, a function and its inverse always, well, almost always, I better say there, intersect on the line y equals x because they are both mirror images of each other about this line. Now, when I said almost always, what I'm really trying to say is that if one of them hits the line y equals x, then the other one is going to hit the line y equals x at exactly the same spot, right? Now, there are some very rare cases where they will intersect elsewhere apart from the line y equals x, but I don't think you really need to worry about those too much. But suffice it to say that if they are going to hit the line y equals x, then that's where they're going to intersect on that line. I know that y equals minus x cubed is a rare case where, as well as intersecting on the line y equals x, there are two other points of intersection. And also the same would apply to y equals minus x to the fifth and y equals minus x to the seventh. There's just a few rare beasties, but to all intents and purposes, I don't think you need to worry about that. If you like, you can just have a fiddle with y equals minus x cubed and see what it does. It's absolutely fascinating when you look at it with its inverse. That's a little segue. Now, we know also that f of f minus 1 of x equals x and f minus 1 of f of x equals x. They are composite functions. Yes, looks like gobbledygook, but it's very true. And I showed you that in video 1G. Okay, another one. If f of x equals x to the n, then f minus 1 of x will be x to the 1 over n, e.g. if f of x was x squared, then f minus 1 of x would be x to the half. Okay, excellent. Functions which are symmetrical about the line y equals x have an identical inverse function. Now that's pretty fascinating. Some examples of those would be y equals x, which is the line y equals x, but more particularly y equals minus x is an example of a function which is symmetrical about the line y equals x, and also y equals 1 over x is symmetrical about the line y equals x. Now, this is a pretty interesting little twist to this. Any translation of the graph y equals 1 over x, where the translations in the x and y directions are identical, in size and sign, S-I-G-N, sign, plus or minus, then basically you are, give you an example of this, you've got y is 1 over x minus 1 plus 1. Now that's been translated plus 1 unit in the x direction and plus 1 unit, in other words identical in the y direction compared to y equals 1 over x. And if I just show you a little graph of that, that's y equals 1 over x, and you can see that that's symmetrical about the line y equals x. Now, after that translation, which I've just enunciated up there, this is what you're going to get. So basically the intersection point of the previous asymptotes was the origin. That's the y-axis and the x-axis. It's been basically translated to a point which is also sitting fair and square on the line y equals x. So if you do that so that the intersection of the asymptotes of a y equals 1 over x graph are going to be still on the line y equals x, basically this new graph is still symmetrical, and you can see it looks still symmetrical about the line y equals x, and therefore, ladies and gentlemen, the inverse is going to be exactly the same as the original. Isn't that something? Yes, it is. Okay, how to find an inverse function graphically? First of all, we're going to do it visually by eye, and then we're going to do some analytical stuff. Okay. Now, I have gone through this in a previous video, but we'll go through it again for the sake of completion and in the context of what we're doing here in this video. So, there are three ways to eyeball, visually by eye, guesstimate the inverse about what it's going to look like. First of all, we take this one here, y equals 2x. Now, this is the first of three techniques. It's the rotate and flip technique. Yes, you heard right. First of all, you swap x and y, right? You see how I just swapped them? Right, that's now x and that's now y. But they're in the wrong place now because y is usually up here and x is usually pointing out horizontally here. So we're going to fix that up so that that's the case again. Restore order to our Cartesian chaos here. So what you do is you reposition the graph into the traditional x and y positions by firstly rotating anti-clockwise by 90 degrees like that. Then you basically have to reflect the whole graph about the y-axis by 180 degrees. Right, now I'll show you. It's better if I show you. Reflect the resulting graph, which now has the y orientated correctly, but the positive x is pointing to the left. See, that's the problem. So we've got to reflect the positive x-axis about the y-axis so that the positive x-axis points to the right, and this is the best way for you to understand it. I'm just going to basically swivel this whole thing, basically 180 degrees, swivel it around the y-axis by 180 degrees, and you will see what happens. There she be. And that's it. And you can see that the new graph is quite clearly y equals x half x instead of y equals 2x. Yes, it's pretty marvellous, isn't it? So the y equals 2x transforms into the inverse y equals half x. Okay? Great. Now, we're going to this is the second way now. The second way is just to bite the bullet and reflect the original function directly about the line y equals x. So this sometimes can be confusing if you've got a complicated looking function. Here we've got y equals 2x, and you can just say, okay, that becomes that one. And that's pretty right, isn't it? It's pretty obvious, but some of them are not quite as intuitive as that. They're sort of going all over the place and curvy and wavy and doing all kinds of weird things, and you've got to really keep your head together when you're working out their inverse. That's the line y equals x, of course it is. Now the third one is the popular favourite, the audience favourite. This is, you take a physical piece of paper, you sketch the original function in the lower right hand corner, like that. Then you basically fold the lower right hand corner with a 45-degree fold, and then fold the paper upwards and look through to the other side where the ink really is now. You're looking through the paper to the other side to see the shape of the inverse. So you're kind of going to have to hold it up to the light to see it. This is what you do. There's the fold, and then what you do when you fold this kind of like forwards and up along that fold there, you will get that looking through. That's pretty good, isn't it? Yes, no wonder it's the showstopper. So that's the third way of visually eyeballing it, right? Now we're going to do some analytical ones now. We're going to find the inverse function of the rule with the function with the rule f of x equals 3 times root x plus 1 plus 3, and sketch both functions on the same set of axes, clearly showing the exact coordinates of intersections of the two graphs, as well as axes intercepts. Alright, that's fine. Now, if you want to revise how to do inverse functions analytically, algebraically, please refer back to video 1G, okay? So here I'm going to do it here for you. This is f of x equals 3 times root of x plus 1 plus 3. And I'm going to use, the range of f will be from 3 and including 3 upwards. That's therefore going to be the domain of the inverse. We need that because we're asked for the inverse function. So we have to quote the function in the inverse function and its domain. Okay, now to find the inverse function, I'm going to use this marvellous little rule here, which I was going through in a previous screen, that f of f minus 1 of x equals x, like that. So what you do there is basically you replace everywhere you see an x in this statement of this function here, that x in there, that little x there, you replace him with f minus 1 of x, okay? That's what we're doing. It's a composite function. So let's see. We have to solve that for f minus 1 of x, don't we? Yes, that's what have I done there? Taken 3 off both sides and divided both sides by 3. Now I'm going to square both sides. And that is it. That is it. Yes, and take 1 away from both sides and you get that. You get that, don't you? Yes, alright, that's the inverse function. That is the inverse function, ladies and gentlemen, right? Now, we're going to find the points of intersection now. Now, there's a really, really big booby trap in this, and I'm going to show you. The way this worked out, it was very fortuitous, because I'm going to show you something of the dangers of trying to solve things for x when you've had to square both sides first. So just have a look at this. A function and its inverse intersect on the line y equals x, okay, because they are mirror images of each other. So basically, if one hits the line y equals x, the other one is going to hit the line y equals x at exactly the same spot. That's just a property of mirror images, and they have to do that. Although otherwise they wouldn't be mirror images. So, okay, so we're going to let f of x equal x, right? F of x equals x. In other words, f of x is this, right, and f of x also equals x. It's easier than solving for f of x equals f minus 1 of x. That'll just get you a dog's breakfast. So we're going to do it this quick way, but it's also got a big danger here. I'm going to show you. See that there? So we're saying that we're going to let y equal 3 root x plus 1 plus 3, and we're also, that's equation 1, we're also going to let y equals x, and that's equation 2. So we're basically going to let the y's be equal, and then we equate the two x expression, the right-hand side expressions. That's what we're going to get. Now, can you see that we're going to have to square both sides to get x sorted out there? Now, when you do that, I've just done that. I've got an NB there. Squaring both sides and solving for x can produce spurious solutions, and spurious they are. So you have to test your solutions in both the equations at the end to see whether they're actually correct for the context of what we're actually doing. I'll give you an example of this. Say, for example, I said to you x equals 2, right? Have you got that in your head? X equals 2. Okay, well, now we're going to square both sides. Therefore, x squared equals 4, doesn't it? Now, if I solve that equation, I could say to you, yes, but therefore x equals plus or minus 2. But that's not right, because x wasn't minus 2. In the first place, it was just plus 2. So the process of squaring both sides and then going back to x again, the squaring both sides has introduced a spurious solution, which became obvious to us when we solved it back for x again. So the same thing can happen in the context of what we're doing here. So we will do it, and I'll show you. Therefore, I've multiplied both sides by 9, yes, and multiplied out the x minus 3 all squared thing, and we're going to cross off those 9s and then solve it for x squared minus 15x, is it? Yes, equals 0. Yes, good. Now we'll take out the common factor of x and we'll get that. Therefore, x equals 0 and x equals 15. However, ladies and gentlemen, we have a spurious solution and a good solution. Okay, you've got to test them. NB, x equals naught is spurious, because if you think about, if you test it, look, you test it up here. When x is naught, what would this tell you? What would this is supposed to be intersection points, right? Intersection points. So when x is naught, that would be a naught, therefore that would be 3 root 1, which is just 3. 3 plus this 3 here gets you 6. So when x is naught, y is 6 in this equation. But of course here, when x is naught, y is naught. So that's not an intersection point. It's not an intersection point. It's a spurious solution introduced accidentally by the process of having to square both sides here. On the other hand, if we test x equals 15, let's do that. That'll be 15 plus 1 is 16. Square root of 16 is 4. 3 4s are 12 plus another 3 is 15. So when x is 15, this y here, this f of x, from this f of x function, which I'm calling y here, that when x is 15, y will be 15, and of course for this equation, when x is 15, y would be 15. So yes, that is a genuine solution, but x is naught is a spurious solution. It's an imposter, right? It's an imposter. So yes, I've said all that there. So when x is naught, f of x equals 6. It's not on the line y equals x, right? But when x is 15, that becomes 15. So that's a good solution. That's fine for our purposes anyway. So the point of intersection must be 15 and 15. Okay? Good. Now, please be careful. Please be careful when you're squaring both sides and getting back to an x solution for x. You better test the solutions in whatever context you've started off with, to make sure it still works, or all of the solutions that you generate all work, okay? Because they may very well not work. Okay, intercepts, right? We've got to do that now. If yes, f of x itself has no x-intercept, because the original graph here has basically been moved upwards and away from the x-axis. Remember, this is a positive square root of x kind of graph. And in its base model form, it would be, if you just had root x, that'd be, the start of that graph would be on the origin, and this one here has been moved back by 1 to x is minus 1 and y is 0, and then this thing here moves it up by 3. See, so it's not even touching the x-axis anymore. Get that? Right, now the y-intercept is when x equals 0. If we substitute x as 0 into the equation, we get, as I was doing up here, this thing here, in finding out the spurious solution, we know that the y value is 6. So therefore the y-intercept is 0 and 6. There's no intercept, and there's a y-intercept of 0 and 6 for our original function, right, f of x. Now that means that the inverse will have no y-intercept. It has an x-intercept of 6 and 0, because it's all swapping x and y, remember? My oh my, and here comes the sketch graph for you. Wow, whoopee-doo, look at that. Incredible. So where's our original? This is our original, where the cusp here, or whatever you call it, the starting point, is at minus 1 and 3, and that over here it's 3 and minus 1. See, everything is swapped. This y-intercept here is 0 and 6, of course, which is an x-intercept of 6 and 0, and here's our intersection point here at 15, 15, right? Beautiful, beautiful, beautiful. Just behold the beauty of maths when you look at that. Nice, isn't it? So, okay, I think we better do another one now. This is looks like a hyperbola. Very hyperbola-ish to me. We've got to express that in this form here, and hence find the inverse function of f of x. Sketch both functions on the same set of axes. Well, we'll do that for sure, guys. Let's go. Right, now there's f of x. Let's do my little fiddle. When the degree of the top is the same as the degree of the bottom, you can do this lovely little fiddle where you make the denominator look like the numerator look like the denominator, like that, right? And then you split those two things off as x minus 1 over x minus 1 minus 3 over x minus 1, which becomes that. It's beautiful, isn't it? So you can see very clearly now that you've got an upside down-ish hyperbola translated over to the right by 1 and up by 1, which sends radar signals into my head, because what did I just say? I said it's been translated over to the right by 1 and up by 1, which means I predict that the inverse function will be exactly the same as the original. There's the original. It's an upside downish one, and yes, we went we've gone over to the right by 1 and up 1, and you can see that the intersection point of those asymptotes is still on the line y equals x. So that's your signal, guys. So when you get the inverse the same as the original function, don't get all confused, like 85% of students do. Don't you do it. You'll know why. So now, proceeding onwards, ever onwards, the range of f, yes, it's everything except where y is 1, as you can see from the visual over here. But that's going to be the domain of the inverse, isn't it? NB, here we go. Compared to y equals minus 1 over x, this function has been translated equally, one unit to the right and 1 unit up, and is still symmetrical about the line y equals x, and hence we're going to find that the inverse is the same as the original function. So let's do it. Let y equal, I always let y equal so I can swap x and y, okay? I ditch the f of x notation just for the process of finding the inverse, and then I go back to it at the end. Right, let's swap. Let's swap x and y, that's what I'm getting, and now I've got to solve that for y, don't I? Y oh y, my oh my. So that's that there. Now if you multiply both sides by y minus 1 and then divide both sides by x minus 1, you can do the whole thing in one fell swoop like that, basically, but that's what you've done. I've just kind of done 2 steps in one, which if you can see, if you add 1 to both sides, you get that. And that is exactly the same. I told you that's exactly the same as the original. Yes, 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 yes. And you do have to specify this? They don't just ask for the rule, do they? No, they ask you for the inverse function, so you have to specify the domain, right? The domain. And it's mighty fine. Now, where's the... Oh, yes. Oh, here we go, through all this boring intersect stuff. Intercepts, I mean. That's y-intercept where x equals 0. Substitute x is 0 into this original up here. It's easier. We'll get plus 4. Now, x-intercept, yes, thank you. X-intercept is where y equals 0, so plugging y equals 0 into that, you would get, multiply both sides by x minus 1, and you'd get 0 equals x minus 4, and therefore x equals 4. Yes, 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 thank you, thank you. And of course you would expect that for the inverse to be the same as the original function. 4's all round here, because basically when you create the inverse, it just flip-flops swapping x and y. So 4 and 0 would swap to 0 and 4. Yes, that's the thing. Yes, I know, it's fascinating. It's absolutely fantastic. So now we'll sketch the graph, and then I think we'll probably be just about finished for now. Here's the graph. Goodness gracious, how wonderful. See, look, 4, 0, 0, 4, because the original graph is the same as the inverse, right? It's symmetrical about the line y equals x. Is that all we need to do? I think it is, isn't it? No other intercepts or anything to worry about? No, I think it's time for the star. Yes, huzzah, the star has arrived. And we feel good because we know how to do sketch graphs, both eyeball and analytically, of inverse functions. So do plenty of practice. Look, they're very important. It's a big, big feature of the course, and you'll get really great at it. So thanks again, and see you later.